Okay, let us start. Nobody is present up to this moment. I hope they will join soon. Now we'll go through another phenomenon of vapor compression refrigeration cycle itself. Which is what we will now examine a vapor compression cycle with superheated vapor before compression itself. So what we have done so far, we have got superheated vapor. We have got a vapor at the entrance of the compressor, which is perfectly superheated and which is perfectly saturated and on the saturated vapor line itself. So stage number one was on vapor saturated vapor line, means the vapor of the refrigerant is perfectly fully vaporized and being going stuck in the compressor itself when it is in totally saturated in the totally saturated state itself, as per the given pressure and temperature. Now, but there are certain other moments we should examine, because we want to know how we can improve the coefficient performance, means how we can increase the length of 4 to 1, length of the stage 4 to 1 evaporating stage with the application of the same length of compression 1 to 2. Means if 4 to 1 is more increased with the same compressor work, so SCOP will increase. Here the vapor compression cycle is superheated vapor before compression is shown in TS, which is temperature entropy diagram. This for S and this for T, where what we see where it is the compressor is in vapor state. The refrigerant is entering the compression when it is in superheated state. But this particular stage is a superheated state. So at the point 1, formerly was the vapor was entering in dry saturated state. Now it's entering in the compressor in superheated state and exit in the compressor in the superheated state again. It state again. Now what happens? This vapor coefficient performance will find out from the result H1 minus H3 divided by H2 minus H1 itself. So in this cycle, heat is being absorbed or extracted in 2 stages. First from point 4 to 1, and then from 1 to 1 dash. The remaining cycle remains same. So heat is absorbed from the surrounding of the refrigerant rods is from 4 to 1 and from 1 dash to 1, 4 to 1 dash, and from 1 dash to 1. 4 to 1 when it is dry stage in when a mixed in a wet stage, means that is mixed with liquid as well as vaporized refrigerant, and it is in that position heat is being absorbed, and when it is superheated and totally vaporized position from 1 dash to 2, it is also heat is also absorbed there. So COP will be accordingly, because work done will be same as H2 and H1. So COP here 1 from enthalpy at the point 1 is equal to enthalpy at the point 4, which is equal to the enthalpy at the point 3 itself. So here the refrigerant effect comparatively more, so COP is supposed to be more itself. Now let us go through one subset itself. A vapor refrigeration cycle, a vapor compression refrigeration cycle plant is working between the pressure limits 5.3 bar and 2.1 bar. Means condenser is working at high pressure at 5.2 bar, and evaporator is acting at low pressure from 2.1, which is given here. Vapor then superheated at the end of compression, and this temperature being 37 degrees centigrade itself. Vapor is superheated by 5 degrees before entering the compressor itself. So vapor at the end of compression, its temperature is T2, that is 37 degrees centigrade, and vapor superheated by 5 degrees before entering the compressor itself. the specific heat of superheated vapor is given as 0.63 kilojoule per kg. So we have to find the coefficient of performance itself. Other things which is given is here pressure, which pressure bar, which is the high pressure of the system, which means pressure at which the refrigerant at gaseous state exits from the compressor and goes to the condenser itself. It is this pressure is the isothermal process, and it is and pressure thus becomes 5.3 itself. So what is given? The pressure here is equal to 5.3 bar, where it is at the exit of the compressor. It is at the point at the stage point 2. It is points to the dry saturated state, reduce temperature, release this temperature and goes to the dry saturated state and reach the point 2 dash of the wet dry saturated line. Then again it loses its temperature and loses its heat or exits its heat, which is given at and reached at the point 3, which is about the wet saturated line itself. So what is being happened in this stage? The temperature compression is start at the point 1, which is superheated state, and finished at the point 2, which is also in superheated state. Then it releases certain amount of reduces certain amount of heat and reaches at the point 2. Then it is and reduces some of the temperature, because at the point 2 to 2 dash is an isothermal process. It has a comparatively it is reducing certain amount of sensible heat, and from 2 dash to 3 it is releasing the heat is as a isothermal process, which at the same temperature 288 here, temperature is here to 288.5 degree, which is it is releasing only the latent heat itself, because heat is being transferred as shown in the entropy chart here. Entropy reduced from 2 dash to 3 itself. So what will happen? The saturation temperature degree centigrade at 5.3, the saturation temperature is 15.5 degrees centigrade. That is equal to given at 37 degrees centigrade. At T2, which is here, that is 37 degrees centigrade plus 273, 310, and T1 is T1 minus T2 dash. It is T1 minus T1 dash is given as only 5 degrees centigrade. Means it is from the saturated condition, it raised to a point 1 by only 5 degrees centigrade itself. The liquid heat at the saturation temperature is given, and latent heat at saturation temperature is also given here at high temperature, saturation temperature 15, at high pressure 5.3. Means this is the enthalpy of the liquid bar at compression at heat exchanger stage, and that the latent heat is being released while reducing from 2 dash to 3. And same is the case of the evaporator, where the pressure is equal to 2.1 and saturation temperature is given as minus 5 degree 40 degrees centigrade. The liquid heat which is being released here at 25.14 and latent heat released is minus 158.7 degrees centigrade itself. So what is given? P1 is the pressure at the fact 4 and 1, which is equal to 2.1 bar, and T2 pressure at 2 dash and 3, that is exchanger pressure, is given as 5.3 bar itself. T2, the temperature at the end of compression, that is given as T2 is equal to 37 degrees centigrade was given, and which is equal to 31 degree Kelvin, and T1 minus T1 dash 5 degrees centigrade. Means T1 minus T1, this rise in temperature, isothermal rise in temperature is equal to 5 degrees centigrade itself. Cp, the specific heat at constant pressure, means that all the specific heat here and here is given as 6.03 kilojoule per kg itself, and T2 dash, which is the temperature of the refrigerant after it releases some of its sensible heat and reaches to the point 2 dash, which is given as 15 degrees centigrade itself, 15.5, which is given here, that is 15.273 plus 288.5 degree Kelvin itself. Just 1 second. Now, what is going to happen here? T2 dash is 288.5 degrees Celsius. So temperature here is given as 310 at T2, and T2 dash is given as 288.5 degrees centigrade, because temperature is given at saturation temperature at saturated state, which means temperature at the line of dry saturation is T2 dash, which is given as 50 degrees centigrade, and it is superheated at the end of compression is 37 degrees centigrade, so it is 310. Now, okay, T1 dash, which is the minus 14 degrees centigrade here, which is given as minus 14 plus 273 is equal to 259 degrees centigrade here. That is 259 degrees centigrade. And at the HF3 is equal to HF2. HF3 is the HF2 dash, sorry. HF3 is the energy of the fluid, enthalpy of the fluid at liquid stage, which is from 1 to 2. It becomes equal to, it becomes same, that is equal to HF3 is HF2, 56.5 degrees, 15 degrees centigrade. The liquid heat which is released here, this being which is both are equal from here and here, as the temperature is not changing. So sensible heat which is present here is equal to 15 degree Kelvin itself. That is 56.15 degree Kelvin. Why it is same? Because the it is no temperature, no sensible heat is being added here. So sensible heat which was present here at the point 2 dash must be equal to the sensible heat at the point 3, which is both are equal to 56.5 degrees centigrade. And HF1 is the fluid temperature at the point 1 itself, at the point 1 dash, which is on the disaturated line, is given as the liquid heat, which is given as 25.12 degrees Kelvin. So what you have got, and HFG means fluid and gas, means latent heat at the point 2 dash, means here is given as the latent heat is given as 144.9 degree Kelvin, and if HFG at 1 dash is the latent heat at the point 1 dash, which is releases latent heat, which is equal to 158.7 degrees centigrade. This is the latent heat here. From TS and TS diagram, what happens? Now TS and phase diagram here, which is brought here, shown here, we have to find out the enthalpy of the point 1, 2, 4, and 3. This 4 enthalpy is required. We have to calculate H1, H2, H3, and H4. So what is going to happen here? The enthalpy at the vapor at the point 1 dash is equal to H1. H1 is the enthalpy at the point 1 dash H1 is the enthalpy at the point 1. So which is the enthalpy at the point of before compression itself. So H1 is equal to H1 dash plus Cp, the specific heat multiplied per unit weight of the refrigerant multiplied by the temperature rise itself. So specific heat minus specific is given as what is in the other side. Specific is given here 0.63 kilojoule per kg itself. So H1, HF1, the enthalpy of the fluid, enthalpy at the point 1 dash when in fluid in liquid state plus the latent heat released from it plus Cp to T1 minus T2 dash. C1 is the temperature here at T2, T1 dash is temperature here multiplied by the specific heat, and at the temperature 1 we have H1 will be equal to with that temperature of the fluid plus latent heat generated there, or the temperature at the point 1 dash will be given by temperature at the point at the fluid state plus the latent heat itself. So we put all these respective values. The enthalpy at the fluid stage is 25.5 and that of the at latent heat at T1 dash is equal to 158.7 plus 0.6 into 5, that is equal to 186.97 Kelvin. So thus we are getting H1 as H1 T1 minus T2 dash is given as 5, Cp is given as 0.63, HF1 plus HF2 is the enthalpy at the point H1 dash, because here we are assume that total refrigerant is being converted to from liquid to gaseous and reached at the point 1 dash itself. So what is happens? 25.12 plus 158 plus 0.63 is equal to 186.96 degree Kelvin itself. Similarly, the enthalpy of the vapor at the point 2 means enthalpy of the vapor at the exit of the compression state, which is given as enthalpy at the point 1 is given as enthalpy at the point 2 is given as H2 dash, means enthalpy at the point 2 dash means enthalpy of the fluid itself at the dry-sectional line, from where it will start releasing its enthalpy, and it will start releasing its energy as a latent heat and will reach at the point 3 here, which is showing that entropy is reduced from 2 dash to 3. Now what happens? HF1 that is H2 plus Cp into T2 into dash. Cp is the specific heat of the vapor itself multiplied with the fall in temperature from T2 to 2 dash itself, which is given here. So what is given? HF2 dash is the enthalpy at gaseous state at dry-saturated state at the point 2 dash, which is the enthalpy at the liquid state plus enthalpy of the latent heat of release of the enthalpy from 2 dash to 2 to 3 in the condenser itself. So we have to add the latent heat at the point at liquid state here at high point, that is 56.5 plus 56.15 plus the latent heat 144.9. So we put it here multiplied by Cp63 210 minus 283, that is 214.6 degree Kelvin. So coefficient of performance of the plant itself is H1 minus HF3 divided by H2 minus H1. So H1 we have calculated as 186, H2 we have calculated 214, and HF3 we have got from the chart, that is liquid enthalpy at liquid state 56.5 divided by H1 is the H2 minus H1 is the temperature we have calculated. H2 is equal to 214 is given here, and H1 is 186.97 given here. So if we put them together and subtract, we'll get the COP as 4.735. Next, let us go to another problem, another critical application. Here it is shown that shown a vapor compression cycle with undercooling or subcooling of the refrigerant. So what is that? What are the four stages of a vapor compression refrigeration cycle? Is 1 to 2 is the vapor compression cycle, 2 to 3 the condenser cycle, where condenser stage where heat is being released from the outside to the outside atmosphere, 3 to 4 where it is the expansion stage where refrigerant is expanding from 3 to 4 dash, and 4 dash to 1 it is the evaporation state where the liquid refrigerant is being evaporated by absorbing latent heat from the surrounding of the refrigerator, refrigerant rods. So here what we are saying, the refrigerant after condensing process to that 2 to 3 dash. Where is the condensing process? This is 1 to 3. 2 is the compression process. 2 to 2 dash to 3 dash is the condensation process, and 3 dash to 4 dash is the extraction process, and 4 to 1 dash is the evaporation process. But here, what is happening? The condensation process 2 to 2 dash is like this. So condensation starts from the point 2 in the superheated state and finishes at the point 3, which is on the wet saturated vapor line itself. But what happens here? Refrigerant after from 2 to 2 dash, it is releasing certain sensible heat and reducing its temperature from 2 to 2 dash until it reaches the vapor saturated vapor line. Once vapor is fully saturated here, then those liquid refrigerant present in the mixture itself. From 2 dash to 3, it is releasing its pressure and is converting vapor refrigerant to liquid state, and this conversion of vapor to liquid is finished not at 3 but at 3 dash but at 3, where it is cooled below the saturation temperature point T3 itself. Here temperature at the point 3 dash and 2 dash is the saturation temperature 3 here, which is where the fluid is totally saturated at this temperature. The fluid is supposed to be saturated into either in the wet state when it is condensed, or it will remain in the gaseous state at 2 dash, but in the same at temperature T3 dash, and releasing heat is being carried out from 2 dash to 3 dash itself. So after condensation, 2 to 2 dash 3 dash refrigerant is again cooled below the saturation temperature up to 3 dash. Next, 3 dash, but is up to 3. Then before expanding by the throttling itself. So it is cooling effect started from 2 to 2 dash, where it is lost some of its enthalpy to the surroundings to reach the saturated line. Then it is in the condenser, feed into the condenser where it is cooled and releases heat, and up to at the point 3 dash where it is stored, it is at that dry saturated line. But again, it is cooling to a certain extent up to point temperature 3 dash, which is not isentropic, not isenthalpic itself. So there is a sensible heat release here and sensible heat release here. 2 to 3 dash heat is released. 2 to 2 dash release heat is released in the superheated state, and 3 to 3 dash, 3 dash to 3 heat is released in the wet saturated vapor line, wet saturated refrigerant line. Sometimes now such a process is defined as Such a process is defined as undercooling or subcooling of the refrigerant, generally done along the liquid line as in shown here. The ultimate effect of undercooling is to decrease the value of condensation of the performance, valve coefficient of performance under the same state condition. Here, more heat is released from 2 dash to 2,3, and thus expansion process will take place. Comparative will absorb less amount of work itself and reach at 4-4 instead of 4 dash itself. So the evaporator line is increased from 1 to 4 dash to 1 to 4 for this type of subcooling effect itself. So how much the process of undercooling, how much it is done, you have to calculate. The process of undercooling is generally brought about by circulating more quantity of cooling water through the condenser by using water cooler than the main circulating water. So to make the subcooling, we have to circulate more amount of cooling water so that we can absorb more amount of heat, or instead of using circulating water, we can use cold water to absorb more amount of heat during the exchange transfer heat exchanger process. This process also brought about employing a heat exchanger. In actual practice, the refrigerant is superheated after the compression and undercooled before throttling. So what is shown here, refrigerant is here superheated. It is superheated region. It is superheated in compression and it is subcooled in the wet saturated line. And cooling it from here by cooling it 3 to 3 itself. The refrigerating thus effect is thus increased by adopting both superheating and adopting both and working as well as undercooling the compressor, referred to a cycle without them. So what happens? Refrigerant evaporated is H1 is H4, but H4 is comparatively less in entropy. What is happening? H1 is equal to H4, and where the temperature at the constant where there is no heat release, only expansion takes place. That is, as adiabatic expansion is takes place from 3 to 4 dash, and it reaches the point 4 here, and here it reaches the 4 dash from the wet saturated vapor line without undercooling, and with undercooling 3 to 4 dash itself. So this line is more than the previous one, 4 dash to 1. That is, more refrigerating effect is being created. In case the refrigerating effect of heat is extracted RE, H1 minus H4, that is H1 minus HF3 itself, as H4 is equal to HF3 at enthalpy of the fluid at point 1, at point 3. As both these are vertical, as enthalpy is even same. Here means HF3 is H4. And in this case, the refrigerated of heat absorbed or extracted is H1 minus H4, H1 minus HF3 itself. And work done is H2 minus H1. That is work done from in the compressor by making the compressor process, that is 1 to 2. So that is W H2 to H1. Thus, COP remains in the same equation, H1 minus H4 and H2 minus H1 itself, where the value of HF3 may be found from the relation itself. And HF3 is HF3 minus Cp to the degree of undercooling itself. Now, let us go through one practical problem. what is given here in the example is a vapor compression refrigerant uses R12 as the refrigerant, and the liquid evaporates in the evaporator at minus 50 degrees centigrade. So lower temperature is given as minus 50 degrees centigrade. The temperature of this refrigerant at the delivery from the compressor is plus 50 degrees centigrade, and where the vapor is condensed at 10 degrees centigrade. So find the coefficient of performance if there is no undercooling and the liquid is cooled by 5 degrees before expansion by under throttling itself. The text specific heat of constant pressure Cp for superheated vapor is 0.64 kJ per kg degree Kelvin, and that for liquid is 0.94 kJ per kg degree Kelvin itself. So what is given? Liquid evaporates at the temperature at minus 15 degrees centigrade. So the lower temperature is minus 50 degrees centigrade. T1 is equal to T1 is equal to T4 is minus 50 degrees centigrade. So that is equal to 258 degree Kelvin. And T2, the higher temperature or temperature at the condenser is given as I'm wrong. The T2 is the temperature of the fluid after superheating, which is equal to 50 degrees centigrade. That is 15 plus 273 to 288 degree Kelvin, which means temperature given here is calculated as well as temperature given here is also calculated itself. Temperature given here from this here and here, both are being calculated here like this. So what happens? What is Cp? Cpv, pressure at constant volume, is 0.64 kilojoule per kg Kelvin, which is given as here the liquid specific heat for liquid per degree rise and fall in temperature is given as 0.94 degree Kelvin itself, and specific heat for superheated vapor per degree rise and fall in temperature is equal to per kg rise and fall in temperature, and per kg is 0.64 kilojoule. So this is for specific heat at when the vapor is in the superheated region. This is the specific heat when the vapor is in liquid state itself. So HF1 from the figure is given as 22.3 kilojoule per kg itself. HF1 is the HF3 or HF1. HF1 22.5 kilojoule per kg means enthalpy at the point 1 when it is in fluid state. From this is the stage and it will reach the fluid stage here. So this is given as, if it is touched here, then H is HF1. Which is temperature at the total saturated liquid state itself, and that is given as enthalpy at liquid state is equal to minus 22.5 degree Kelvin itself, only 20.5 degree Kelvin itself, and HF3 dash, which is the temperature at the point 3 dash is here, which temperature at the temperature of the liquid and liquid refrigerant at high temperature area or condenser area. So here it is given as high temperature area is equal to 10 degree. That is given as 45 degree, 45.4 degree Kelvin itself. Okay, so HF3 is the temperature at the point 3 dash at 45.1 degrees centigrade, means this is the temperature at high temperature. This is the enthalpy at high temperature when the temperature is here more or less 10 degrees centigrade, and HF3 3 dash is the enthalpy at the point 3 dash itself, and here or here itself, from the point here or from the point here. HF3 dash is 44.5 degree Kelvin, which is the temperature of the fluid at the height at this point here, which is on the wet saturated vapor line, and given us wet enthalpy at high temperature. So what is given here? Temperature at 10 degree and liquid enthalpy is 14.4. So that is being sent here as HF3 dash itself. And H1 dash 182.8 degree Fahrenheit, because it is at on the vapor line. It is given as minus 50 degrees centigrade, which is a lower temperature, but on the vapor line, this enthalpy is given as 180.8 degree Kelvin itself. H2 dash is the enthalpy given at higher temperature, means at 10 dash, that is equal to H191 degree centigrade. SF1 0.904 kilojoule per kg degree Kelvin, means entropy at the point 1 at the when it is a liquid state itself. And HF3 is the entropy at the point 3 when it is in liquid stage, means HF1 is here entropy at the point R, and HF3 is entropy at the point here itself. So in PS and TS diagram, TS and PH diagram itself, TS and PH diagram, there is no undercooling as shown in the figure, and thus respectively X1 is the dryness factor of the reactor at the point 1, means at the point 1, what is the dryness fraction, what is the value of what is the amount of refrigerant present at the point 1 itself. So S1, entropy of the point 1 will be the entropy of the fluid at the point 1, which is entropy of the fluid refrigerant at point 1 plus X1. HFG is the entropy of the fluid, is the latent heat of the fluid between the section 1 to 2 itself. Latent heat is being absorbed from the surrounding, which is the difference in enthalpy. HFG SG1 minus SF1, and difference between the entropy at the point 1, when one is gaseous state, one is fluid state. So it is given as SF1 is 0.09, entropy of the liquid state 0.0904, and HF3 is the temperature at the vapor state 0.7054. Both are given, and we got S1 in terms of X1 itself. Now, what is entropy? S2 at the point entropy at the point 2 is given by the formula entropy at the point 2 dash on there, which is the entropy at dry saturated line at the point 2 dash is 2 dash plus 2.3 degree temperature specific heat of the vapor refrigerant multiplied by log T2 divided by T2 dash. T2 dash is the high temperature from which the temperature is reduced to T2 dash itself. Thus, the entropy thus created can be have this formula, which is given S2 dash is given entropy at vapor state at high temperature or high temperature and pressure, that is 0.629. High temperature and temperature under pressure 0.629 and 0.692 plus Cp is given as coefficient of thermal expansion. Now, specific heat at constant of the vapor enthalpy, which is given here, saturated vapor, which is given 0.064 kilojoule per kg. So we put it here, 64, and temperature at 2-2 and temperature 2- is given. We have converted it. So this is 288 divided by 283 log. So after calculating, reducing the calculation, after making the calculation, simplifying the calculation, entropy at the point 2 is given as 0.734. Since the entropy at the point 1 is equal to at the point 2, so this equation where S1 is supposed to be equal to S2 itself. So we can have this point as 0.734 is equal to this portion of the earlier equation itself, and thus we got the specific heat at in the liquid state. So not specific, but the dryness fraction, the amount of vapor present is almost 997%. Almost it is vaporized at the point 1 itself. So 1 is kept here. So X1 or specific or the dryness fraction at this point 1 is available. So the enthalpy at the point 1 is equal to enthalpy at H1 plus F1 enthalpy of fluid at point 1, entropy of the fluid liquid represent at point 1, and plus dryness fraction of multiplied by the latent heat of conversion of the liquid itself. So if it is 96% converted, then it means 99.7% vapor is being converted. So this is given at this here and put the value of latent heat, which is the difference between the temperature enthalpy at gaseous state minus enthalpy at the fluid state in lower temperature or lower pressure light itself. So H1 we have got 180.4 kilojoule per kg itself. So we have got the enthalpy. We have got H1 here, and H2, the enthalpy at the point 2 in the superheated stage is equal to H2 dash enthalpy H2 dash plus CPV, means specific heat of the vapor refrigerant, and plus T2 minus T2 dash itself. T2 dash is the temperature at the superheated temperature of the vapor. T2 dash temperature is at the dry saturated vapor. So we put 191.76 plus 0.64 is equal to 288 minus 283. That is 194.96 kilojoule per kg itself. Thus, what happens here? Specific heat. See, both this H1 and H2 is available. So H1 minus HF3 dash, which is at 45 degrees centigrade, and initially there is no undercooling here, which is shown here. So I put the value of H1 minus HF3 and H1 minus H2 is equal to 9.27. But there is no undercooling. Now, let us go through the another cases. The coefficient of performance when there is an undercooling of at 5 degrees centigrade, which is given in the problem here. First, there is no undercooling, and number two, the liquid is cooled by 5 degrees centigrade before the expansion or throttling. So before going to the throttle valve or expander, it is cooled by 5 degrees in the second part of the problem. So what we are doing here, we have to find out. We see the cycle remains same here. One is on the wet region, and so there is some specific heat, and two is on superheated state, that is known to us. 2 dash we have calculated, and now it is after releasing the heat exchanger, it is up to a certain extent up to the 0.3 before feeding to the expander itself. So what is happened here? The enthalpy of the liquid refrigerant at 0.3, which will be equal to HF3 dash. HF3 is HF3 dash is represented at 0.3 dash minus the coefficient specific heat at the liquid refrigerant minus multiplied by degree of undercooling itself. This is giving us already 0.94 multiplied by the 5 degree undercooling and the enthalpy at the 0.3 dash, which is the enthalpy at the liquid state at high temperature. So we have got the enthalpy here as 40.7, which is equal to HF3. We put the value of HF3 is 40.7, and we put the other values H1 and H2 as we have calculated, already calculated. This enthalpy will be, this COP is 9.59. So with what we have found here, enthalpy without undercooling, COP becomes 9.27, but with undercooling somehow increased to a certain extent, which is equal to 9.59 itself. Let us go through this problem. Example 14.4. This simple NH3 means ammonium vapor compression refrigerant system has compressor with piston diameter, piston displacement of 2 meter cube per minute. Means the volume of refrigerant being compressed is equal to 2 meter cube per minute itself, and the condenser pressure is equal to 12 bar, means high temperature of the system is 12 bar, and evaporative pressure is 2.5 bar, means low temperature of the pressure. This liquid is subcooled by 20 degrees centigrade by soldering the liquid line to suction line itself. The temperature of vapor leaving compressor is 20 degrees centigrade, but it is superheated by 20 degrees centigrade. Heat rejected to compressor is compressor cooling water is 5,000 kilojoule per hour, and volumetric efficiency of the compressor itself is 0.8. So please compute the capacity, indicated power, and COP of the system itself. So at the compressor, volumetric displacement given as 2 cubic meter per minute. So P2 pressure at the point 2, at the point 2, at the point 2 dash, at the point 2, 3, at the point 3. All three is 12 bar. So this is a straight line. So pressure is 12 bar at high pressure region. P1, P4 pressure at the point 1, at the point 4 is given as 2.5 bar. T3, 20 degrees centigrade. 20 degrees, T3 is the 23 degrees centigrade. It is the temperature at the lower region. 20 plus 273, that is equal to 293 degrees centigrade. It is subcooled by 20 degrees centigrade. That is 293 degree Kelvin. And T2, that is the temperature at the end of compression, which is equal to as high as 100 degrees centigrade, which is equal to 273 degree Kelvin. And volumetric efficiency is 0.08. Means compressor has a volumetric density 0.80% itself. Thus, through this TS and pH diagram, what we see, entropy, enthalpy, TS diagram, TS. So temperature at 1 is given. We have put the temperature at the point 2, that is the end of compression, that is 273 degree here. At the point 2 dash to 3 dash, that is the high temperature of the system itself, which is starting from the dry saturated line in the condenser and releasing at the wet saturated line at condenser itself. That is 2 to 3 dash. That is equal to 303. Which is given here, and then it is subcooled to a certain extent, subcooled to a certain extent as 293 here by 20 degrees centigrade. So it is 293 here, and temperature at the lower side is given as T2, that is T1 itself, which is also given here. So what is going on? The pH diagram, the evaporated temperature corresponding to 2.5 bar means higher bar, is lower bar is equal to the lower pressure T1 is equal to T4 dash is equal to minus 14 degrees centigrade. So minus 14 plus 273, that is 270.59 degree Kelvin. So here we put the value of lower temperature of the system, 259 degree Kelvin. Condensation temperature is going to 12 bar, means higher pressure. Condensation temperature is T3 and T2, T2 dash and T3 dash, which is given as 30 plus 30 plus 273, 703 degree Kelvin itself. Specific volume of dry saturated vapor is 22.5 bar. That is at 0.1. This is the 0.1 specific volume, means volume per unit volume per kg of the dry saturated vapor is given 0.449 to meter cube per degree Kelvin. So what happens? The enthalpy of dry saturated vapor at 0.1 is given as 1428 H1, and that the superheated heater is given as 16.30 kilojoule per kg. And enthalpy of the subcooled liquid at 20 degrees centigrade at 3, SF3, at is H equal to H4. In the enthalpy at the entrance of the evaporator is 273 kilojoule per kg. Then mg, mass flow of the refrigerant in kilojoule per kg throughout the system. So the piston displacement Vp